Okay, so we're going to pick up immediately where we left off in class. So let's take a quick second to do a review of what we were doing. So just to kind of tie it in, as I said, because this is a lot of material. So we start off with this idea of a unit circle. And now it's called a unit circle because once we understand the way these functions behave, in the simplest case as we define them, and then we can understand how they're going to behave in other more interesting cases. So the idea is that we're going to set up a circle, and we're going to tell you that the radius is r is 1, right? So the radius is 1. Now we're going to start off by laying the radius directly on the x-axis, and if radius is 1, then this point is going to be 1, 0. So this is, the x is 1 because I've gone 1 in the x direction and I haven't moved at all in the y direction. Now I'm going to take a unit or a length of t units. Again, I like to think of them as strings. And so I have something of t units. Now, of course, if you wanted to, you could write this point as 1t, right? Because you're still only 1 unit away from the center in the x direction, but then you've moved t units up. Now we're going to take this, we're going to lay this across the edge of the circle. Now what that means practically is that we're going to end up with an arc length s such that s is equal to t. All right, so now that we have this s equal to t, we can make us a fun little triangle and say, all right, I'm going to move in the x direction to this point, and then I'm going to move in the y direction to get up there. Now, this point we define as P, and we're going to say that the x, we're going to call it A, and the y, we're going to call it B. So this is just a point, and we get to that point, again, by moving A units in the x direction and B units in the y direction. But this point actually allows us to create a triangle. So I'm going to draw my triangle here, right? So this is B, this is A. Now this hypotenuse we actually know because this golden piece right here is touching the edge of the circle. That means that it has to be the radius, and we know that the radius is equal to 1. So doing this, we have that, well, let me take a step back. We can create all the trigonometric functions, but before we do that, we're going to say, if we know that s equals r theta, and we know that r is equal to 1, and s is equal to t, right? The idea is that we've laid this t across the triangle, or excuse me, across the circle, and that gives us an arc length of s. We get that t is equal to theta. So I can write sine theta equals sine t, cosine theta equals cosine t, and tangent theta equals tangent t. Now, sine is opposite over, and this theta in question is right here. So sine is opposite over hypotenuse, so this is b over 1, which is b. Cosine of t is adjacent over hypotenuse, so this is a, and the tangent is opposite over adjacent, so this is b over a, right? Given the way I've written it, I have to make sure that a is not equal to 0. All right, so what we're trying to do here is this allows us to do something really interesting. So if I know that P is equal to AB, right? AB is just is the coordinate, but I know that A is along the x-axis and B is along the y-axis, excuse me. But of course, I know that this B is equal to sine of t and this A is equal to cosine of t. I can write this as cosine of t or theta and sine of t or theta. So in this way, I've essentially turned this geometric object, a circle and a triangle embedded inside, into a coordinate system. And this allows me to do all kinds of really fun things. Now, we're going to go back to our special points, because on our unit circle, if the radius is 1, the radius can lay against the x-axis, against the y-axis, against the x-axis in the opposite direction, or the y-axis in the opposite direction. So in this case, we've gone over the one radius, which is 1 in the x direction and 0 in the y direction. This is 0 in the x direction, 1 in the y direction. This is -1 in the x direction, 0 in the y direction. And then 0 in the x direction and -1 in the y direction. So in this case, we can say that sine of theta, I'm going to do cosine first. So cosine theta is equal to 1, sine theta is equal to 0. In this case down here, we have cosine theta is equal to 0, and sine theta is equal to -1. Up here, we have cosine theta is equal to 0, and sine theta is equal to 1. Here we have cosine theta is equal to -1, sine theta is equal to 0. Okay, now here's where we are. We know these angles. These angles are really specific. This is 90 degrees, another 90 degrees, another 90 degrees, and another 90 degrees. Or similarly, we can write this as pi over 2. So the idea is that we start out at 0, and we go pi over 2, we end up top. We go another pi over 2, and we end up right here, another pi over 2 down here, and then another, and we're back here. So I'm going to call this upper point, this is pi over 2, or 90 degrees. This is pi, or 180 degrees. This is 3 pi over 2, so I'm going to write 90 degrees here. And this is 2 pi, or of course 0 degrees. So these are really special angles that allow us to define the domains and range of sine and cosine. So the idea is that sine and cosine, the domain is going to be all real numbers, because anything that I put in there is just, I can convert it into some kind of measurement of radians, right? Something weird like 12 over 32, I could convert into something that looks like pi. Again, that would be a weird number, but I could do it, and all that would mean is that I then just go around my circle that radian, right? That radian measurement. So that's going to be okay. So this means that sine, I'm going to say the domain of sine and cosine is all real numbers. So I'm actually going to put this superscript r, which means all real numbers. Now, how about the range? So the idea is that these max out, the highest it can possibly be is on one of these 4 corners here, right? If I end up with something, a point here in blue, well, remember that my cosine is going to be this blue piece right here, and my sine is going to be this green piece. Oh, excuse me, that was the hypotenuse. That's going to be 1, right? And the sine is going to be this green piece. So this is my sine theta. This is my, in blue, my cosine theta, and that's going to be less than 1. So the idea is that, I'll put this in purple because this is going to be my radius. So the idea is that, and I'm going to make the point black here. Yeah, make sure we make sure to have all these colors right. Okay, so my sine, of course, is going to be my b, which is my y. So it's this vertical piece. My cosine is going to be my x, or my a, which is the horizontal piece. Now, both of these are less than 1. They're less than the hypotenuse, which is the radius, which is 1. So this means that the range of sine and cosine is -1 to 1. They can't be any bigger on this. Obviously, when you have instances like, okay, if I have, 6 sine or something like that, then my range for 6 sine theta is -1, or excuse me, -1 times 6, -6 to 1 times 6 is 6. So, we can take these functions and shrink them and grow them, and that's fine. But unit circle, the point of the unit circle is that this is the standard way in which we're going to understand these functions. And then once we understand them, in the simplest case, we can make them all kinds of wild. We can do all kinds of cool stuff with them. But the general idea is that they max out at 1 and min out at -1. So if we know the tangent of theta is the opposite over the adjacent is equal to sine theta over cosine theta. So cosine theta can be 0, and that's going to be a problem. So when is cosine 0? So cosine theta is 0 at, well, it's 0 at pi over 2 and 3 pi over 2. But of course, if we understand that you can just keep going around the circle. If I, for example, have 5 pi over 2, that means I've gone all the way around, and I'm going to go 1 extra pi over 2. So 5 pi over 2 also makes cosine 0, which makes tangent undefined. So we write this as the domain of tangent is all real numbers except n pi over 2, where n is an odd number. So any, oh, excuse me, 6 is not odd, 7, so on and so forth. So any number that's odd is going to give you, it's going to have you go around this circle and then go a little bit more, right? And similarly, we wrote it like this, but this also works if you want to go the opposite direction, right? So like negative pi over 2, right? If you go negative pi over 2, that's the same as going this direction down to 3 pi over 2, right? Pi over 2 and negative 3 pi over 2, you end up in the same place, which makes it undefined. And we're actually going to get to that in a second, talking about periodicity and stuff. So what about the other functions, the co-functions, right? The cosecant, secant, and the cotangent. So the easy one, since we already talked about cosine is 0, if we know that secant is equal to 1 over cosine, this means that the domain of cosecant, or excuse me, of secant is all real numbers except n pi over 2, where n is equal to 1, 3, 5, 7, so on and so forth. Again, we just got that from sine. Now, let's look at cotangent. So cotangent theta is equal to the adjacent over the hypotenuse is equal to cosine theta over sine theta. So when is sine theta 0? Well, if we look over here, it's 0 at any multiple of pi, right? If we start at 0, sine is 0. If we go full pi across, we get sine of 0. If we go 2 pi, we're back at 0, 3 pi, 4 pi, so on and so forth, right? So this is n pi, where n is equal to just any integer. So what that means is that the domain of cotangent theta is all real numbers except n pi, where n is equal to 0, 1, 2, 3, so on and so forth. Now, since we talked about sine, we can talk about cosecant. So cosecant theta is equal to 1 over sine theta. So the domain of cosecant theta is equal to, I'm just going to write it as, is all real numbers except n pi. N is equal to 0, 1, 2, 3, so on and so forth. So these are the domains. Now the ranges were relatively straightforward for sine and cosine, right? We determined that they max out at 1 and they min out at -1. But how about the range of cosecant and secant theta? Well, if cosecant is just 1 over sine and secant is 1 over cosine, that means that, when cosine is a really small number, then, or excuse me, when, I don't want to say this, when cosine is, say, 1, well, then you just get 1 over 1, right? If cosine is less than 1, then say cosine is 1/2, then you have 1 over 1/2, which is equal to 2. So since cosine is only good between 0 and 1 or 0 and -1, remember that if you take a number 1, like we did with 0.5, you take a number 1 and you divide it by something that's less than 1, you get a bigger number. So for example, cosine is 1/2, 1 divided by 1/2 is 2. Cosine is -1/2, 1 divided by -1/2 is -2. Now, as cosine gets closer to 0, you have a number from either direction. Cosine could get close to 0 from the negative direction or from the positive direction. So what that means is that you have a number 1 divided by something that's getting increasingly small. Well, this actually blows up, right? This actually blows up to positive or negative infinity. So because cosine can get arbitrarily close to 0, and secant will be defined, or sine can get arbitrarily close to 0, and cosecant will be defined, we can say that it's going to be anything, so the range of cosecant and secant is cosecant or secant can be greater than or equal to 1, or cosecant theta, secant theta, less than or equal to 1. So the question is, can it be anything less than, can it be, for example, less than, this needs to be -1, less than 1, for example. Can cosecant ever be 0.5? Well, the answer is no, because sine maxes out, cosecant. Can cosecant ever be 0.5? So sine maxes out at 1. So 1 divided by 1 is just 1. And if sine is anything less than 1, then again, you have 1 divided by a number less than 1 is going to be greater than 1. So that's why you can't have a cosecant be 0.5, because sine is only going to be between 0 and 1 or 0 and -1. So cosecant can't be 0.5 and it can't be -0.5. Same with secant. Secant can't be 0.5 or -0.5 because cosine is only between 0 and 1 or 0 and -1. In which case you get the same thing. 1 divided by a number less than 1 is greater than 1. And it just maxes out. When cosine maxes at 1, you just have 1 over 1. Or when cosine maxes or mins at -1, you have 1 divided by -1 is -1. So these are a little bit unintuitive. You may think about it, the number line looking like this. This right here is -1 to 1, and the secant and cosecant functions can take on any value in this direction or any value in this direction. But because of the way that they're defined as 1 over something that is varying between 0 and 1 or 0 and -1, you actually can't exist here. And that gives us the range of cosecant and secant. So at this point, we've done the range and the domain of all of the functions except the tangent and cotangent. We have yet to actually do the range. And the range of the tangent and cotangent are a little bit different. So the range of tangent theta and cotangent theta are, so let's think about this. In the case of tangent and cotangent, you've got something varying between -1 and 0 and 0 and 1 divided by something else varying between -1 and 0 and 0 and 1. So you end up with a pretty similar situation that you have
with cosecant and secant, in that the bottom is going to blow up as it gets closer to zero from the negative side or the positive side. But the top isn't just one, right? With cosecant and secant, the top was always one, so that's why you couldn't exist in this green area here. But in the case of cotangent and tangent, the top piece actually can be, can be zero. We imagine, if sine is zero and cosine is one, right? That happens. Let's look up here. So that happens at pi over 2, right? So pi over 2, you have at 2 pi or 0. So at 2 pi or 0, you have cosine is 1 and sine is 0. So your tangent would be 0. Similarly, if you jump over to your theta equals pi, you've got your cosine is -1 and your sine is 0, so you get 0 again. The idea being that because the top can actually vary, the top of this fraction can vary, you can end up getting numbers between -1 and 1. But it's important to note, going back up here, that as you get closer to one of the special points, one of the corner points, you'll see that one of the trigonometric functions is heading to 0, and the other is heading to is heading to 1 or -1, right? So in this case, actually, when the cosine, in the case of tangent, when the cosine is heading to 0, sine is actually heading to -1 or 1. So that means that you've got a number that is getting increasingly close to 1 or -1 being divided by something that is getting increasingly close to 0, so it blows up. And it's the opposite for cotangent, right? As sine approaches 0, cosine will approach -1 or 1, so you've got something approaching -1 or 1 divided by something approaching 0, it blows up.
So what that means is that our range is actually -infinity and infinity. And it's for the same reasons that the cosecant and secant blow up as well, because you've got something on the denominator that goes to 0. Now, as you get to calculus, you're going to find this all the time. If something on bottom is getting increasingly small, unless the thing on top is also getting increasingly small, it's just going to explode, either positively or negatively. So that gives us our ranges and domains of these various functions. Now, there's a really great table on page 589, which goes through these, or goes through these more succinctly. But here, we've actually gone through and shown where they all come from. So if you have any questions about this, then let me know in class on Monday. So the next thing we're going to talk about, we've mentioned this word multiple times, but the periodicity of the trig functions is really useful. So we determined that if you start in a circle, you start here, and you go in a circle. If you go around 2 pi, you start back where you were. So anything less than 2 pi and you're somewhere different, right? Pi over 2, you end up here. Pi, you end up over here. 3 pi over 2, you end up down here. But any multiple of 2 pi, and you're going to end up with the exact same thing. And this is true for both sine and cosine, right? If I start here, I have some cosine value, right? This is some point, which we'll write as cosine theta, sine theta. And if I go 2 pi around, I'm back. I go 4 pi around, I'm back. 6 pi, so on and so forth. So what this means is that sine of theta plus 2 pi k is equal to sine theta. And similarly, cosine of theta plus 2 pi k is equal to cosine theta again, right? If I go a full circle, I end up exactly where I started. So this k is equal to 0, 1, 2, so on and so forth. And this is a fancy way of saying that if I go around the circle once, I'm back where I started. If I go around twice, back where I started, so on and so forth. So this helps us to define the concept of a fundamental period of a periodic function. So if f is some function such that there exists a p and such that theta plus p is just equal to f of theta, right? The idea being that this p doesn't actually change what f of theta is, we say p is the fundamental period of this periodic function. So in this case, p is equal to 2 pi, because sine of anything plus 2 pi is just going to be that same thing. Similarly with cosine. Now, because sine and cosine have this periodicity, that also transfers to cosecant and secant. So cosecant and secant also have the same period of 2 pi. The idea being that cosecant of theta plus 2 pi is just equal to secant of theta plus 2 pi is equal to secant of theta, and cosecant of theta plus 2 pi is equal to cosecant of theta. Now, tangent gets a little bit weird. Tangent is a bit different, and cotangent. So with tangent, consider this. So we know that this right here is 1, 0, 0, 1, negative 1, 0, and 0, negative 1, right? Perfect. So what happens if, remember, the tangent of theta is equal to the opposite over the adjacent? So at this point right here, we have tan theta is equal to 0, right? Because it's 0 over 1. Here we have tan theta is undefined because you have 1 divided by 0 over negative 1 is 0. And this tangent of theta is equal to an undefined value. So cotangent is going to be the same, but it's going to be flipped, right? So here, this cotangent of theta is going to be undefined. Here, the cotangent of theta is equal to 0. Here, the cotangent of theta is undefined. And here, the cotangent of theta is equal to 0. Now, what you should notice is that instead of it taking a full 2 pi to end up at the same value for tangent and cotangent, you actually only need 1 pi in order to end up with the same value, right? If you start at 0 pi, you get tan theta is equal to 0. If you go a full pi, you get tan theta is 0 again. You go another pi, you get tan theta is 0. Similarly with cotangent. So what this means is that tangent of theta plus k pi is equal to tangent of theta, and similarly cotangent of theta plus k pi is equal to cotangent of theta. So this means that the period, or fundamental period, So we'll say the fundamental period of tangent and cotangent is just pi. So what does even and odd mean? So let's draw us a quick circle and play around with some values. Often do our unit circle here. And let's see what happens. So supposing that I choose pi over 4 and I get sum a b. Now what happens if instead of pi over 4 I go negative pi over 4? Well, it turns out that I get the same a, right? I've gone the same, I'm going to use my my colors again. I've gone the exact same a in both cases, but I've gone negative b, right? So I have gone b and I've gone negative b, but I've gone a in both cases. So I end up with a and, I'm going to rewrite that, a and negative b. So this is kind of interesting. So this says that if I have sine of negative theta, well, this is equal to negative sine of theta, right? The idea is that this b is the same value, whatever it is, and it's my sine theta. But if I go in an opposite direction, I end up with the same value, but a negative sign, right? I went pi over 4 and I ended up with this b. Now I go negative pi over 4 and I get negative b. So this makes it, if we remember a definition from algebra, a function is even if f of negative theta equals f of theta, and odd if f of negative theta equals f equals negative f of theta. So in this case, sine is therefore odd. How about cosine? All right, so let's consider yeah, well, we'll just consider the same thing that we already have written. So if I have sine of pi over 4, I get a. And if I have sine of negative pi over 4, I get a. Excuse me, let me take a step back. I meant cosine. I have cosine of pi over 4 is a. And then cosine of negative pi over 4 is also a. So this means that cosine of negative theta is just equal to cosine of theta. So cosine is even. Now because we know, that cosecant, secant, tangent, cotangent are all related to sine and cosine, just inverses and fractions and stuff, we can actually go through and figure out, if cotangent and tangent or secant and cosecant are odd or even, just by setting it up in this way, and we'll find that that it turns out to be pretty simple to do that. And so page 590 has the full table, so I recommend that you go check that out. But just to kind of show you, how you would fill out this table, supposing that I do cosecant of negative theta. Okay, so cosecant of negative theta is equal to 1 over sine of negative theta, but sine of negative theta is of course equal to negative sine of theta. So this is negative 1 over sine of theta is equal to negative cosecant of theta. So therefore, cosecant is odd as well. And so if you would do, cosecant is going to be odd, secant is going to be even, and then you can play around with the tangents, but the tangents turn out to be odd as well because of the sign. The sign actually makes them odd. I'll go ahead and show that real quick. So tangent of negative theta equals sine of negative theta over cosine of negative theta equals negative sine of theta over cosine of theta equals negative. I'm just going to rewrite it like this. And therefore, we have tangent of negative theta equals negative tangent of theta, and you get the same thing with cotangent of theta. Therefore, they are odd.